Good morning. Let's go ahead and get started. Just a very quick announcement. I don't know how many people were planning to come to my office hours today, but I need to cut them short. So they're just going to be from 2 to 2:45. If that's a problem for anybody, just send me an email and we'll meet later down the week. Exam 2 is coming up next week. So the first review session is this Friday. Please come prepared to the review session, and the study aids we've talked about previously have all been posted. All right. So the last time that we met, we completed the math chapter. Basically, what we've done is we've introduced a total differential or total derivative. Basically, that tells us that for a given function, we can look at how that function changes due to changing parameters or variables independently. We also introduced something important called the cross derivative. And we saw that if the cross derivatives are equal to each other, that means that we have an exact differential. That correlates with a state function. If I have the cross derivatives not being equal to each other, then I have an inexact differential, and that corresponds to a path function. We also showed that we could use total differentials with other equations to get some identities, and we're going to build on that a few chapters into the future. All right, we have redefined the change in the enthalpy, and then we have introduced the first law of thermo, which basically says energy is conserved. So the change in energy of the universe over all time is expected to be zero. Because we're primarily going to be interested in looking at specific systems, then we say our system's energy change is going to be due to energy transfer due to heat or due to work. All right. And then we talked about sign conventions, and it's very important to be understanding of what these mean. So if a gas expands against an external pressure, that means it's pushing against a force. It's doing work. So from the system point of view, that work is negative. Right? If it compresses, that means the surroundings are doing work on the system. The energy of the system goes up due to that energy transfer, and that's a positive change with respect to energy. Right? We've seen this integral before, 1 over x. Integral of 1 over x is natural log of x. We're going to be using that today. Let's see. So things that we're going to look at today, we're going to look at expansion and compression or pressure volume work. Along the way, we're going to look at units and bars, decimeters cubed. We're going to come up with a convenient conversion between that and joules. And then over the next few lectures, we're going to see over and over again that work is a path function. So that's going to be pretty straightforward. We're also going to talk about reversible work. Remember last time we said that if we have a reversible process, that means that every step of the way, an incremental change in one direction can be getting you back exactly where you started if you reverse incrementally. Okay? And that's an important concept that we'll be applying when we talk about work. All right? So from there, we're going to talk about calculating the reversible work, and then we will see that energy for a number of examples. Energy we expect to be a state function. Of course, showing it that it's a state function here and there doesn't prove that it's always a state function, but every example that we look at will demonstrate that for those examples it behaves as a state function. So only the initial and final states are important. All right, and then we'll talk about heat and work transfer for reversible isothermal processes. All right. Okay, some other things I wanted to just talk about. So just a reminder, we have said on numerous occasions, an ideal gas's energy depends upon the temperature and the number of particles. If I hold the number of particles constant, then it only depends upon the temperature. All right? And where we're going to see this is important is we go back to our definition of heat capacity. That means heat capacity is, by definition, du dt. I can rearrange this equation and say du is equal to Cv function of t, help me out, dt. Okay? So anytime that I want to calculate the change in the energy of my system, I know that I'm going to have to look at this. And this also explicitly states if dt is equal to 0, what's du? It's going to be equal to 0. Okay? All right, the other identity I just wanted to introduce very quickly, and I should have done this weeks ago. We've previously said that the definition or the connection between R and the Boltzmann constant is Avogadro's number, all right? So to make this a more generally applicable equation, I'm going to just say, well, if I want to know the number of moles, N, that's going to be the number of particles over, help me out. This is number of moles, right? So this is particles. How do I get from particles to moles? Avogadro's number, all right? So these are equivalent to each other, all right? So I can multiply both sides of this equation by an equivalency. So that's going to get NR, all right? And then in this case, that's going to be N over NA, right? Because that's the same as N. We see NA's cancel, and I'm left with NKB, all right? So this is important because this basically says N times the Boltzmann constant is the same as the number of moles times the gas constant, okay? Any questions before we move forward? All right, where are we going to go? So what we're going to do is we're going to start by talking about pressure, volume, work, all right? So we're going to think, just generically first. So this is a gas in a container. We see that I have some little pins there holding the lid, right? If I pull those pins out, we see that it is expanded. We agree? Okay? All right, and before we go forward with this, let me ask this question. So it's clear that we have some mass up here, right? And I'm moving the mass up. So has this system done work, or has work been done by this system or on this system? It's done work, all right? What's the sign of W for that? It's negative for the system point of view. We all agree? All right, so trying to make this into an equation, I've got this mass here, all right, that's working on this. And we know from physics that the force experienced by this gas, this system, is going to be equal to the mass times the gravitational constant, G. Okay? All right. And if I'm talking about work, that's an energy change. That's going to be force times distance. And for our example, that's going to be m times g, mass times the gravitational force. And I'm moving this up, and I'm going to call this distance h. Okay? Right. And this, again, should be very much review from physics. So my mass is positive, my gravitational force constant is positive, h is positive, and therefore I need to put a negative sign in front to reflect the fact that I know that if I expand, it's a negative value. We all agree? All right, the other thing that we recognize is that this is a three-dimensional world, and there's a piston there that has an area associated with it. Okay? So we're going to call that area A equals area of piston. Okay? And what I can do is I can take this equation and multiply it by A over A. All right? That's 1, right? This is m times g. That's my force. That's area. What's force over area the same as? That's the same as pressure, right? Minus P. Force equals mg over A. Okay? All right, and in this case, what I'm left with is this height times an area. What's height times an area going to get me? That's a volume, right? And this reflects a change in a volume, right? So I'm starting from this volume, and I'm ending at that volume, all right? So that's delta V. Make sense? All right. All right. So what we can say in this case then is that work is going to be minus P delta V. And we expect that work to be negative. And that's because we're doing an expansion. The system is pushing against the surroundings. It's expanding against an external force. It's expending energy, so it's done on the surroundings. Okay? All All right, so this works, what we've derived works as long as this is a constant mass sitting up there, right? I have a constant force on it. To generalize this, we're going to say P dV, all right? And then what we need to do is we need to integrate it from V1 to V2, and then we need to put the negative sign in there to indicate that when it's expanding, it's going to be a negative change in energy. Does that make sense? All right. And then given this is our general definition of work, under the circumstances where our pressure, external pressure, is constant, then we can pull that out in front of the integral, and that becomes minus PEXT then times delta V. Okay? But that's only because this pressure is constant and I can pull it out front. Okay? All right, and then the other thing, and this should be pretty obvious, but for me to do an expansion, that means my internal pressure has to be greater than the external pressure, right? Because if the two pressures are the same, you're not going to get any movement. We agree? And if the external pressure is less than the internal pressure, you're not going to get an expansion, you're going to get a compression. Does that make sense? Okay. All right, and then if we look at this side B, we have a situation where, again, we've got this external force. We've got the pins on the underside. I pull the pins out and I see a compression. That means the surroundings have done work on the system. And what's the sign of W going to be for this case? It's going to be positive, okay? When pins are removed, compression occurs, work is done on the system by the surroundings, and work is positive with regards to the system point of view. Okay? Make sense? All right, well, let's do some calculations and some examples. So what we're going to start with is we're going to be talking about compression and expansion of a gas under isothermal conditions. All right, so isothermal means my temperature is held constant, right? And this curve, you may recall, corresponds to the isothermal curve for an ideal gas, all right? And because we're limiting our discussions to ideal gases, what we know is that at every point on that curve, the pressure times the volume is equal to nRT, which is a constant. So we can say that P times V is a constant. And that defines this curve. Does that make sense to everybody? Okay? All right, so explicitly for this example, what we're going to look at is a compression from 1 decimeter cubed. So that's sitting at that point. And then we're going to compress to 0.5 decimeter cubed, that point. All right? And we're doing this isothermally, which means the gas has to exist on this isotherm if I'm not changing the temperature. Okay? Does that make sense? Okay? All right, so the first thing that we're going to do in order to determine under what circumstances I expect this compression to occur, we need to calculate what the external pressure limits are. All right? So I'm going from 1 decimeter cubed, starting at this pressure, this volume, right? I want to end up at this point. And it should be pretty clear that if my external pressure was the same as this pressure, I'm not going to get any change, right? And so that means the external pressure has to be greater, right? Because I want a compression, right? And the isotherm basically tells me that this is the minimum pressure that will get me, or the maximum pressure that will get me that compression. Okay? Does that make sense? Right. So we can ask, what's the minimum pressure that we need in order for this pressure to occur? Well, what we can do is we can say, well, we know P1 V1 equals P2 V2 as long as we're talking about an isothermal process. Okay? And because what we're interested in knowing is the external pressure, P2, that's going to be given by P1 V1 over V2. Right? From there, I just plug in the numbers that are provided in the problem. So for P1, where are we? At 1 decimeter cubed. That's going to be at 2 bar. So I have 2 bar. 1 decimeter cubed. And I divide that by my final volume, which is 1 decimeter cubed. And that becomes 2. What did I do? Oh, yeah. Which one's supposed to be a half? The bottom one. Thank you. 2 over 0.5. And that's going to equal 4. All right. And if we see our units cancel appropriately, so it's to be 4 bar. All right. Which is nicely consistent with what we see in our figure. Right? Make sense? Okay. Next up, we are going to say, well, we're going to perform this compression at an external pressure of 4 bar. And we're going to do this compression in a single step. And that means we should be able to calculate the work that has occurred. All right? So we know that work is going to be equal to minus P delta V. All right? Because we have a constant external pressure. Make sense? Okay? All right. So this is going to be minus 4 bar. And then my volume change, my final volume will be 0.5 decimeters cubed minus 1.0 decimeters cubed. All right, and if I perform that calculation, that's going to come out to be plus 2 bar decimeter cubed. All right? Okay, because this is an energy transfer, we want to be able to put this in joules. So we need to do some unit conversions. All right? And so for the unit conversions, what we can say is that we know that 1 bar is the same as 10 to the 5th pascals. And 1 pascal, SI unit, is 1 kilogram per meters squared per second squared. All right? And then from kilograms meters squared per second squared, I need to get rid of decimeters. We know that 10 decimeters is the same as 1 meter. And I cube that. All right. Now I'm in SI units, so I can say 1 joule is 1 kilogram meters squared per second squared. All right. And whenever I multiply that all through, that gets me a value of 200 joules. Okay? All right, now we don't want to have to keep doing this conversion over and over again. And if you work it through, you can find that 1 bar decimeter cubed is the same as 100 joules. So that gives us a nice, easy conversion factor between bars, decimeters cubed, and joules. Make sense? Okay? All right, so we've established that we have a value of 200. It's a positive value. That should make sense. We're compressing the gas. Work's being done on the gas. The only thing I want to do is say, well, if I wanted to determine graphically the amount of work, how could I determine the amount of work for this example? That's P, right? That's delta V. So it's the area of this box. Everybody follow that? Okay. Area equals work. Okay? All right. Let's do a little bit of a thought experiment. All right? So this is the situation that we've looked at. We basically have this external pressure, right? We've got these pins. We open the pins, and it's compressed to 0.5, right? We've gone from 1 decimeter cubed to half the volume. Okay? Now, if I had put pins down below here, it doesn't matter what this pressure is. If it's greater than 4, I still get the same compression. We agree? Yep. So I could double that pressure. I stop it here. And because I'm confined to the isotherm, my initial and final conditions from the point of view of the system are absolutely identical. Right? We agree with that? Is the work going to be the same? Well, let's choose to say that we're going to use an external pressure of 8 bar. All right? I have the same change in the volume, and we clearly see that we're going to end up with an additional amount of work, right? But from the system point of view, it looks exactly the same. It's got the same final volume, temperature, number of particles, and pressure inside, okay? We good? All right, and that's what's shown here. So in this second case, we've basically shown that this is the work. This area corresponds to the work whenever we have an external pressure of 8, okay? And one of the things that we see is that how I do this compression, that is, whether I choose to have a larger external pressure or a smaller external pressure, very much determines the change in the energy due to the work. And so what we can say is that work depends on the external pressure, so therefore, work is what kind of a function? Does that make sense? Okay. So now, let's think about this. I think I want to talk about the graph first. So in this example, we saw that we maximized the amount of work that we needed to do by using an external pressure of 8 bar, right? And if I wanted it higher, I could increase that external pressure. Now, if you think about a practical point of view, in general, if you're trying to design an engine or whatever, you want to minimize the amount of work that you need to do in order to get work out. Does that make sense? So you want to minimize the work of compressing, and you want to maximize the work that you get out of the system. Does that make sense? Right? That's, increasing efficiency. So by think about doing a compression, the minimal effort possible, I'm going to start at this point, and then I'm going to say, well, in order for me to get some compression, I have to incrementally increase the pressure, right? And I have to do it again, and I have to do it again. And if I'm doing it isothermally, that means I'm basically going to follow this curve. Does that make sense? All right? And if I'm doing it incrementally, what kind of a process are we defining? Step, equilibrate, step, equilibrate. What's that called? Anybody? So we're doing it so that we're infinitesimally changing, and we're every step of the way, if I go backwards, I get exactly where I was before. Yes? That's a reversible process. Okay? Does that make sense? All right, the minimum amount of work needed to compress a gas occurs when the pressure is infinitesimally greater outside than inside the vessel. And the system follows the pressure volume isotherm, and this is called reversible. Okay? And so in this next section, what we're going to do is talk about reversible work. All right, so this will be work and reversible processes. Okay? All right. I also want to take a moment to just talk about doing, rather than a compression, an expansion. So we're going to start from point 1, go to point 2 in that direction. Let me put pressure and volume here. Okay? All right. And we're going to do an example of this calculation-wise momentarily, but I want to talk it through. So if I wanted to do a single-step expansion from this volume to this volume, I know that my external pressure has to be less than the internal pressure. And if that's where I want to end up, right, that means that my pressure has to be at that value or lower to get the expansion. We agree? All right? And if I said what's the, maximum pressure that I can do that at, that's going to correspond to that value, right? And in this case, because we're expanding, we're doing work, right? So what's the sign of work? It's going to be negative from the point of view of the system. And this area would give us the single-step expansion work that we can get. Does that make sense? All right, so that's doing it in one step. Pretty straightforward. Now, if I wanted to maximize the work that I get out of the system, then I'm going to start at this point, and I'm going to say, all right, I'm going to expand a little bit. So I'm going to infinitesimally decrease the pressure. I'm going to do it again, and I'm going to do it again. I'm basically going to do it reversibly, right? That's what I'm saying. And that means that I can trace out this entire area. And that will represent the maximum work that I can get out of the system. Does that make sense? Right? So the reversible process gets me the minimum work that I need to drive a compression and the maximum work that I can get out of the system for an expansion. Okay? We good? All right, and then we've already said this a couple times. All right, the maximum amount of work obtainable from the expansion occurs when the pressure is infinitesimally smaller than the pressure inside the vessel. Right? The big caveat is, because we're doing this incrementally, we're changing pressure by an infinitesimal amount, that means that it's going to take an infinite amount of time. So we'll just say forever. All right? So as such, this represents a theoretical limit. Right? So theoretically, that's the maximum work I can get out of the system, or the minimum work that I need to put in to drive the process. Okay, just a little bit of an aside here. Because we're talking about an ideal gas, we can describe the state of the system using the ideal gas law. And if we look at this, what we see is that we've got three variables and a constant. So that means if I want to specify the state of my system, I need two of those three variables, right? And that's all I need in order to define absolutely where my gas is. Okay? All right, so we're going to do another example. We're going to calculate the amount of work done upon expanding isothermally against a constant external pressure. All right? And what we want to do first is determine what the maximum pressure is. So I'm going to draw my isotherm, because we're told that it's an isothermal expansion. So I've got pressure in bar, I have volume in decimeters cubed. I'm just going to draw on a generic isotherm, which doesn't look all that good. All right. All right, so we're going to start from 0.5 decimeters cubed. We're going to end up at 1 decimeters cubed. What we're told is we're initially at 4 bar. Right. And we've already talked about this a little bit. So I know that as long as my external pressure is below this value, I'm going to be able to get that expansion. Right? So if I put external pressure equal to 0, I would get that expansion. Right? I want to find out the maximum pressure that permits the full expansion. Because it's isothermal, we again will say P1 V1 equals P2 V2. I'm interested in knowing what the pressure is at the end of this expansion on the isotherm. Okay? Let me just write that over there. That's going to be P2. That's what we're interested in. And then P1 V1 over V2. In this case, our initial pressure was 4 bar. Our initial molar volume is 0.5 decimeters cubed. And then I divide that by the final volume, which is 1 decimeter cubed. And that comes out to be 2 bar. Okay? All right. And so we can expect to see this expansion occur as long as my external pressure is 2 bar or less. Okay? All right, and if I do the work for that, if I do this in a single step, what I know is that that work's going to be this area, right? And that area will correspond to, right? So I'm going to go back to basics on this. Our definition in general, integral, negative the integral from V1 to V2 of P dV. For this example, the pressure is held constant, so I can pull that out front, P external. And then I've got the integral from V1 to V2 of dV, and that's going to be the same as delta V. So minus P external delta V. All right? And at that point, now I just plug in numbers. So this is going to be minus 2.0 bar. And then my volume change. My final volume is 1 decimeter cubed. My initial is 0.5 decimeter cubed. Right? And that will come out to be minus 1 bar decimeter cubed. Right? And then in getting that to joules, I'm going to convert from bar decimeters cubed to joules, and the conversion factor is 100 joules. Right? So let me just write that out. So 100 joules, 1 bar decimeter cubed, and that comes out to minus 100 joules. Okay? All right, so the area of this portion of our graph is 100 joules, and it's negative because we're doing an expansion. Does that make sense? Okay? All right, so now we have got a quiz for the day. We're going to work the first problem together. That is work for step 1. And then the second part, I'm going to give you a couple minutes to work on your own, and you'll get credit for getting the right overall answer. Can you pass one behind you? And we'll give you guys 2, okay? Okay, so in this particular case, we're going to do the same overall expansion, but rather than doing it in a single step, we're going to do it in 2 steps. All right, so looking at our isotherm, so I have pressure in bar, I have volume in decimeters cubed, drawing my isotherm, all right? So we're told step 1, we have 4 bar, 0.5 is the molar volume, all right? We're going to be expanding against a constant pressure of 3 bar. And that will get me to 0.667 decimeters cubed. All right? So there's step 1, there's step 2. We're going in this direction. And then step 3, we're going to be expanding against a pressure of 2 bar to get us to a final final volume of 1 decimeter cubed. Okay? All right, so initially, we're going to be moving. This is our initial point, starting point. Our external pressure is 3. We're expanding from here to here. That means that that area is going to correspond to the work of the first step. We all agree? Okay? So work for step 1 is going to be given by minus P external times delta V. In this case, that's going to be minus, our external pressure was 3 bar, and our delta V will be 0.667 decimeters cubed minus 0.5 decimeters cubed, and then I'm going to multiply that by 100 joules over 1 bar decimeter cubed. And that gets me a final value of, I don't remember off the top of my head, minus 50 joules. And so that area is minus 50 joules. Okay? Oops, and I didn't draw the box in the right place. That area. Okay? All right, so what I would like you to do is the second part. So take 2 minutes and solve the problem for step 2. Are you guys done? Thank you. All right, I'm going to give you 30 seconds to finish up. Thank you. Thank you. Could you grab the one from behind, please? Thanks. Thank you. Thank you. May I? Perfect. Thank you. You done? All right, so I have everybody's, right? So the full worked out answer will be given to you in the annotated lecture notes. For now, what we can say is that second step came out to minus 67 joules. The first two steps together, minus 50 joules plus minus 67 joules, giving us a grand total of minus 117 joules. Okay? All right, so one thing to point out is that we indeed have seen that we get more work out of the system by breaking up into multiple steps. And that's consistent with us at the other limit going to a reversible process. Because if I broke it up into 2 steps, I've got more work. If I broke it up into 3, I'd get more still. And to maximize the amount of work I can get out, I'm going to break this up to an infinite number of steps from this point to this point, which basically means I follow this curve. Does that make sense? Okay. All right, so the work performed is greater than if we had performed it in a single step. We've pointed out that the maximum amount of work is going to be associated with a reversible process. And then we have to ask the question, how can I calculate that maximum amount of work? Okay? All right, so for reversible isothermal compression expansion of a gas, I'm going to start with our definition of work for expansion and compression. So I have the integral V1, V2 of the pressure times dV, right? So we need to determine the pressure dependence on the volume then, all right? So what I can say is that P is equal to nRT over V, right? So I substitute that in for the pressure. It's going to be minus integral V1, V2, nRT over V dV, right? Now it's important to step back and say, well, we recognize that we're doing this in an isothermal manner, right? So temperature is going to be a constant. It comes out in front. We're not changing the number of moles of gas, so that's a constant. So this becomes minus nRT integral V1, V2 of dV over V, right? So we'll have minus nRT, and the integral of 1 over V, natural log of V, and that needs to be evaluated between V1 and V2, so V2 over V1, right? That's a pretty important expression, right? And if you think about where we've derived it from, it's an ideal gas, and it's isothermal, right? Okay? All right, let's do a quick example. So we're going to be talking basically about the example that we've used previously, single-step expansion, two-step expansion. Now we're going to say, how about we let it be reversible, right? So in this case, what I know is that work is going to be given by minus nRT ln V2 over V1. And then you step back and you say, okay, I want to calculate it, but boy, I don't have the temperature and I don't have the number of moles. But what do we know that this is the same as? That's the same as the pressure times the volume anywhere on the isotherm, right? So P1 V1 equals P2 V2 equals a constant. All right, so for our example, we can say minus P1 or 2 V1 or 2, you just need to make sure that they match, times the natural log of V2 over V1. And for this particular example, I'll go ahead and plug in values. So it's going to be minus, we'll choose P1. So we're 0.5 decimeter cubes at 4 bar. So this will be 4 bar times 0.5 decimeters cubed, right? I'm going to go ahead and do the unit conversion. So 100 joules is the same as 1 bar decimeter cubed. And then I have to take the natural log of the final volume over the initial volume. So that's going to be 1 decimeter cubed over 0.5 decimeter cubed. And that's basically it. And then the final value that we calculate is minus 138 joules. Okay? And what we see is that this is greater than if we did it in a single step or 2 steps or 3 steps. This is the maximum that we can get out of this particular expansion. Does that make sense? Okay, so let's summarize some things that we've talked about. Work is a path function. How we choose to do our expansions and compressions depends on how we do it. Or that determines how much work we have to put in or we have as output. When we're talking about an expansion, work is maximized if we do it reversibly. If we're talking about a compression, the reversible process gives me the minimum work to drive the compression. And then the final portion of this is to recognize that because we're doing it reversibly, infinite number of steps, infinitesimal changes in pressure, that means it takes forever. Okay? So it really reflects a limit. All right, next section. We'll talk about the first law of thermo. And we will state U is a state function. All right. And this just is some reminders that we covered whenever we were talking about partial differentials and total differential equations. So we know that work and heat are path functions. So when we integrate them, we get W and Q. We don't get delta W. We don't get delta Q. All right? That's important. And to indicate that it's a path function, we put delta instead of D for our infinitesimal change in work and heat. All right? But because the energy of the system is a state function, then we can say that the integral from state 1 to state 2 will be our final energy of the system minus our initial energy of the system, or delta U. Okay? All right, so this really means we can write our first law of thermo in 2 different forms. Right? One is to do it differentially. An infinitesimal change in the energy of the system can be caused by an infinitesimal change in energy due to heat transfer and an infinitesimal change in energy due to work. Okay? Right? And then if I integrate both sides of this, that gets me the integral form, which is delta U of our system is given by the heat transfer in or out and the energy transferred in or out in the form of work. Okay? Okay. So before we move forward, I want to just remind us, I want to think something through here. Right? So I'm going to draw on the board if I can find something. We've been talking about isothermal expansions and compressions, right? So we're going from point 1, point 2, right? Isothermal means I'm on this curve. So let's think about that. Because it's isothermal, that tells me that delta T is equal to 0, right? And because delta T is equal to 0, what can we say about delta U for our system? It's a function of U and T. U is a function of T and N only. So if we're holding the number of particles constant, that means delta U has to be equal to 0. We agree? Okay. So let's write one more thing. Delta U of our system equals Q of our system plus W of our system. We agree? All right, so if I go from point 1 to point 2, I've done an expansion, right? So that means the system's doing work. What's the sign of W? It's negative, right? And it's doing work. But if delta U is equal to 0, what does that tell me has to also be happening? I have to have heat flowing into the system to compensate for the energy flowing out in the form of work, right? It's very important to recognize that, and it's exactly equal to each other. Does that make sense? Right? And this should make sense globally, so let me just point it out that way. So my system's going from this point to the next. We know that it's expending energy. It's decreasing energy by producing work, all right? In order for the energy of the system to stay constant, for every joule I output, I have to input 1 joule in heat, okay? And if I didn't let that heat transfer occur, what would happen to the temperature of what's inside my system? If I only did an expansion but didn't let heat transfer, temperature is going to change. And which way is it going to change? All right, let's think about it. So my system is doing work, so it's going from one energy state to a lower energy state, right? So that means the energy is decreasing. How does that show up in terms of temperature? It would decrease. Does that make sense? Conceptually, that's a pretty important thing to recognize, all right? Let me just end by talking about, let's just define adiabatic. How many people have heard of adiabatic before? All right, so that's good. Adiabatic processes mean Q is equal to 0, right? So if this was a perfect vessel, it does not allow heat transfer in or out of the system. So what occurs inside of there is adiabatic. Okay? That's where we'll leave it for today, and we'll see you guys on Wednesday. Okay. All right. This little figure, very important. We're going to use it throughout this chapter. It's going to show up in future chapters, so become familiar with it. And might it show up on the exam? Have a good one.